Hi everyone. Today we are going to be covering section 8.9 from the textbook, which talks about improper integrals. Improper integrals are going to be any integral where we have to deal with infinity at some point in the integral. So kind of the most obvious example of this is if our bounds of our integral are going to be infinity. So for example, if we have the integral from 1 to infinity of 1 over x dx, or we have something like the integral from negative infinity to infinity of e to the negative x squared dx. Both of these are going to be improper integrals because they do have this positive or negative infinity in the bounds of the integral. The other instance where we have improper integrals is if the function actually evaluates to positive or negative infinity at some point in the integral. So for example, if we have the integral from 0 to 3, 1 over x squared dx, right at this bound of 0, I have a 1 over 0 squared, which is going to look like an infinity, right? The graph of 1 over x squared looks like this. And so we can see as we get closer and closer to 0, we are going upwards to infinity. So this is also going to be an improper integral. Another example would be something like negative 1 to 3 of 1 over x squared still, because we do have this value of 0 in the middle of our bounds. So the place where the function will go up to infinity does not necessarily need to be one of the bounds, but if it is one of the bounds, this still counts as an improper integral. Now, there are a couple of reasons why we're interested in improper integrals. The first reason is that they do actually extend our definition of what an integral is, right? It takes this thing that we have and it extends it to where we can deal with infinitely long intervals or functions that might not be continuous. And so it allows us to do this operation of integration on more functions. The second reason that we're going to be interested in improper integrals is that in section 9, I think 9.4, I believe, but one of these sections in chapter 9, we're going to use these improper integrals in order to find things out about other mathematical functions. And so we will be using this very soon for these types of problems as well. So they're very relevant in the next couple of sections in the textbook as well. Okay. So the big idea with dealing with these types of integrals is to replace the infinities or the negative infinities with variables and then deal with limits instead. So the idea for just the most basic case where we have the integral from a to infinity of f of x dx, what we're going to do is we are going to replace this infinity by a variable b. So we have the integral from a to b, and then we will take a limit as b goes to infinity of f of x dx. And so what this is going to allow us to do is it's going to allow us to actually plug in this b value right here. B is a variable in for our bounds, and then we can look at limits of this as well, right? Because infinity, negative infinity, these aren't real numbers, and so we can't just go plug them into our equation. We need to deal with variables instead. And so this is kind of how this idea works, is it allows us to work in the realm of variables instead of positives or negative infinities. So just kind of as a quick refresher on a couple of the limit rules you would have learned in Calculus 1, we'll just really need two of them. So the limit as x goes to a of f of x plus g of x. So if we're adding two functions together, we can just take the limit of both of these and add them together. So f of x plus the limit as x goes to a of g of x. And finally, if we have the limit as x goes to a of c times f of x, so we're multiplying everything by a constant, we can pull the constant out in front. So very similar to the rules we have for dealing with integrals, f of x. Okay. So let's just jump straight into an example for how to solve this most basic case of problems. So as an example, let's say I would like to evaluate the integral from 1 to infinity of 1 over x squared dx. Great. Well, using our definition, we have the limit as b goes to infinity of 1 to b 1 over x squared dx. Now the integral of 1 over x squared, this is the same as x to the negative second, so we will get negative x to the negative first. So this is still limit as b goes to infinity of negative x to the negative first from 1 to b. Right, and now we're at a point where rather than plugging in infinity or negative infinity, we have this b variable here we can plug in instead. So this is the limit still as b goes to infinity of, now what happens when we plug in b, we get a negative 1 over b, and then we have minus a 1 to the negative 1, which is 1, so this is a positive 1. Okay, great. So now we can use our limit rules to split up this integral. So the limit as b goes to infinity, and we'll pull a negative out of 1 over b, plus, well, the limit as b goes to infinity of 1 is just going to be 1, right? This 1 doesn't depend on b in any way whatsoever, so the limit won't affect that. Now, if we think about it, if we plug in a really, really, really big number for 1 over b, we're going to keep getting smaller and smaller answers. So, for example, 1 over 10 is 0.1, 1 over 100, 0.01, 1 over 1,000 is 0.001, and so on and so forth, right? So as this b goes to infinity, the limit as b goes to infinity, we're going to have this 1 over b getting closer and closer to 0. And so this limit is actually going to be 0 in this case. And so we have a negative 0 plus 1, or 1 as our final answer. And this is really interesting, right? So we took this area that we're looking at, and it has an infinitely long width to it. However, we're claiming that it has a finite area, even though it has an infinite width, which is really interesting. Infinity very rarely behaves kind of how you would expect it to. And this is very similar to the Gabriel's horn argument we talked about in the surface area section, where there are these kind of weird 3D shapes that can have an infinite surface area but a finite volume. You can kind of think about this in the exact same way, where we have an infinite width but we still have a finite volume. So in general, if we have an indefinite integral, improper integral equals a real number. So in this case, it equals 1, equals a real number. We're going to say that it converges. Otherwise, so if we have an answer that's going to be positive or negative infinity, if we have an answer that just does not exist for whatever reason, you'll see this a lot in trig functions, we're going to say that it diverges. So otherwise, it diverges. Okay. So let's do another example, and now let's do one with a negative infinity instead of a positive infinity in it. So we're going to approach the negative infinity the same way, but now rather than having our b value get bigger and bigger and bigger, we're going to have it be more and more and more negative. So we're going to define the integral from negative infinity to a f of x dx as the limit as b goes to negative infinity now of b to a f of x dx. Going straight into another example here, let's consider the integral from negative infinity now to negative 1 of 1 over x dx. Right, so by what we were talking about before, this is going to be equal to the limit now as b goes to negative infinity of b to negative 1 over x dx. Great. Keep this limit outside. The integral of 1 over x is going to be the natural log of the absolute value of x. And we are going to evaluate this from b up to negative 1. Plugging in our values, right, we still have this limit as b goes to negative infinity of now natural log of 1, right? We took the absolute value of negative 1, which we know is going to be 0, and then minus natural log of the absolute value of b. So this is the limit as b goes to negative infinity of negative natural log of absolute value of b. No parentheses. Right, and if we think about this and we keep plugging in bigger and bigger and bigger values for b, right, this is what happens when we take our absolute value sign. We're now dealing with positive numbers instead of negative numbers. We're going to keep getting bigger and bigger and bigger function values out. And right, we're never going to kind of hit this ceiling we get when we deal with limits, right? There's no horizontal asymptote for this natural log, right? The graph of natural log looks like this. But as we keep going out to the right here, we're going to keep getting larger and larger y values. So this limit here is actually going to be equal to a negative infinity, right? The negative comes from the negative in front of the natural log of b here. And so we say that this integral right here is going to diverge, right? It's not going to be equal to some real number. It's equal to negative infinity in this case. So in this case, we do have an infinite width, but we also have an infinite area to go along with this infinite width. Okay. So kind of the third case that we talked about right in the beginning and that we haven't covered yet is going to be when we have some integral where the bounds are now negative infinity all the way up to positive infinity. So we're just integrating over all of the real numbers. So to deal with this, we're going to use a very similar technique with one additional step where we kind of break this integral into two different pieces. So the integral from negative infinity to infinity of f of x dx is equal to the limit as b goes to a negative infinity of b to a f of x dx plus, the limit now as c goes to positive infinity from a to c of f of x dx, where a is just going to be any real number. So pictorially, what's happening in this case is if we have some picture, we might be taking the integral of this function, and we pick our a value here. What we're doing is we're saying, okay, this rightmost sum here is going to be the integral to the left of our a value. So that's going to be all of this total area right here. And then this right part is going to be all of the area to the right of this a value. So that's going to be all of this right here. And this is why we can pick any a value, right? We can kind of split up this integral however we would like to. Now, generally, the best case is going to pick an a value of 0. The reason this is that if you do have functions and you're trying to plug in a number for it, it's almost always easiest to pick 0 as the number you would like to plug in. So as a general rule of thumb, picking a as 0 is a good choice. So as an example of this, let's deal with the integral from negative infinity to infinity of dx over 1 plus x squared. Excuse me, my allergies are acting up. Okay, so I'm going to take my own advice. I'm going to pick my a value as 0. So this is the limit as b goes to negative infinity. Integral from b to 0 dx for 1 plus x squared. And the limit as c now goes to positive infinity from 0 to c dx 1 plus x squared. All right, so at this point, you could either recognize, possibly from a table or somewhere else, that the integral of 1 over 1 plus x squared is the tan inverse. You could also prove this using a u substitution as well. That would be a great way to do this problem, right? A u substitution, specifically a trig substitution for this problem to get the tan inverse. Either way would work for this, but we're just going to recognize that this is going to be the tan inverse. So we have the limit as b goes to infinity of tan inverse of x evaluated from b to 0, and still this limit as c goes to infinity tan inverse of x from 0 to c. Tan inverse of 0 is going to be 0. 0, so this means we actually have negative limit as b goes to infinity, negative infinity of tan inverse of b plus limit as c now goes to positive infinity of tan inverse of c. Now, if we remember what our tangent function looks like, so tangent function right here, we can see that as we keep getting bigger and bigger and bigger x values, we are getting closer and closer and closer to this horizontal asymptote of pi over 2. And similarly, as we get more and more negative x values, we're approaching this horizontal asymptote of negative pi over 2. And so what this means is that our final answer is negative of negative pi over 2 plus pi over 2, which simplifies to pi. Right, and this is extremely interesting. I have this integral of 1 over 1 plus x squared. There is no pi's in this. There's no sines. There's no cosines. And so it's really interesting that when I do take this area, I'm going to get a pi out of it. And this is just kind of one of the many places in math where pi seems to come out of equations that we're not really expecting it. And this happens all the time, not just in integrals as well. But the area under this curve is going to be pi. Great. All right, so we're going to deal with one more quick-ish example of where one of the bounds is positive or negative infinity before we move on to unbounded functions. So specifically, we're going to look at integral from 1 to infinity, 1 over x to the p dx, where p is a real number. So this could be p is 14, p is negative 3, anything we'd like for p. And the reason we are looking at this integral in particular is it's going to come up in the next chapter. We're looking at whatever section we use these improper integrals again. And so we're just going to deal with actually figuring out when this integral converges and when it diverges right now. Okay, so what we would like to do for this is we do need to break it up into two cases. The first case we're going to do is when p equals 1. And the reason we split up p equals 1 and p not equal to 1 is that when p equals 1, we're going to get a natural log, and when p does not equal 1, we do not. So integral from 1 to infinity, 1 over x dx, right? This is same as before, limit as b goes to infinity, 1 over b, 1 over x dx. The integral of 1 over x is natural log, infinity of natural log of x evaluated from 1 to b. Natural log of 1 is 0, so we get the natural limit as b goes to infinity of the natural log of b. And as we talked about before when we dealt with 1 over x previously, this limit is going to go all the way up to infinity. So this is infinity, and so for p equal to 1, it is going to diverge. Okay, so what about other p values we might be interested in? So p not equal to 1. And in this case, we have 1 to infinity of 1 over x to the p, right? Rewriting this as a limit as b goes to infinity to b. Don't forget your dx is 1 over x to the p dx. Well, now we can just use our exponent rules to rewrite this integral. So this is going to be the limit as b goes to infinity of x to the negative p plus 1 over negative p plus 1. And this is evaluated from 1 to b. Okay. Just plugging things in, we have the limit now as b goes to infinity of b to the negative p plus 1, negative p plus 1 minus 1 over negative p plus 1. Okay. So what this is all going to come down to at this point is this negative p plus 1 right here. If this negative p plus 1 is positive, plus 1 is positive, right? We have b raised to some positive number. It could be 1/2, it could be 13, but either way, as we keep taking b bigger and bigger and bigger, right, we're raising bigger and bigger and bigger numbers to some positive power. And so this limit here is going to go to infinity. So then the integral diverges. Rewriting this in a bit nicer way, if I add the p to both sides, I have p less than 1. The integral is going to diverge. And since I already know from above that for p equals 1 it diverges, I actually get for p less than or equal to 1, the integral is going to diverge. And the opposite case, so now I have negative p plus 1 is less than 0. Well, then I have a really, really big number raised to a negative exponent. Negative exponents is the same as taking reciprocals. So I have 1 over a number going off to infinity, which means that this left part of the sum is actually going to go to 0. And so in this case, the integral converges, and it's going to converge just to this part right here, this 1 over 1 minus p. And then just rewriting this is the same as p greater than 1. So we have a complete classification of when this integral is going to converge and diverge, and actually what values it's going to give when it converges. So just kind of keep this in the back of your mind, and we're going to use this in a couple of class periods. Okay. So moving on to the second type of integrals that we are dealing with, which is where the function is going to be unbounded on the domain of the integral. So as what we are going to do in this case is we are going to do a very similar technique where we introduce this new variable, and we are going to then take limits of that as well. Okay, so I'm just going to jump straight into this with an example, and then we can talk about the general cases for this. So the example we'll be dealing with is going to be the integral from 0 to 1 of dx over the square root of x. Right? And we can see from this that this 0 is going to be a problem because it would mean we are dividing by 0, which is something that we don't want to do in this case. And so we are going to take a limit as b approaches 0 from the right. The reason we're going to be approaching from the right is that we have values just from 0 to 1, and so we don't want to put in negative values in for our limit here. We just want to put in positive values. So the domain we're interested in is 0 to 1. And if we're approaching from the left, right, we're putting things over here. We would have negative square roots, which is something that we don't want. So we're going to be approaching from the right in this case. So this is b to 1, still of dx over x to the 1/2. Okay, so taking integrals, this is the limit. B goes to 0 from the right. X to the negative 1/2 turns into 2x to the 1/2, or 2 square root of x, still evaluated from b to 1. And we get that this is limit b goes to 0 from the right of 2, square root of 1 is 1, so 2 minus 2 square roots of b. And this is great, right? We aren't dividing by zeros, so this limit as b approaches 0 from the right of this 2b is going to be 0. So this is actually equal to 2. Great. And so that's going to be the answer for our integral. So kind of as a more general case of how this works for these problems, we dealt with the case where the a value, this lower bound right here, was going to be the place where it blows up to infinity. And so in that case, we're going to do this limit approaching from the right. In the case where our top value is going to be the value where it blows up to infinity, we're going to approach from the left with this limit as c goes to b from the left. And then the final case, which we're going to do an example on, is if the integral is in, or the place where the function is not continuous is in the middle of our function. And in that case, we're going to break this up into a very similar way we did for positive and negative infinity, where we have two different integrals. In this case, the place where we break it up is going to be given to us. It's going to be the place where the function is discontinuous, but we still do have this splitting up process. So to kind of demonstrate how that works on an example, let's consider the integral from 1 to 10 of dx over x minus 2 to the 1/3. Now, The problem point for this function is going to be in x equals 2. The reason this is if I plug in x equals 2, I'm then dividing by 0, which means the function is either going to go to positive or negative infinity. And so I'm going to want to split up the integral on things to the left of this 2 value and things to the right of this 2 value. So what this is, consulting the chart above, this is going to be the limit. Now as c approaches 2 from the left, integral from 1 to 2, or sorry, 1 to c, excuse me, dx over x minus 2 to the 1/3, plus now approaching 2 from the right, d approaches 2 from the right, the integral from d to 10 of dx over x minus 2 to the 1/3. So what we're doing in this case is we are taking the line 2 and we're taking, everything to the left of 2, and limit approaching from the left, and everything to the right of 2 with this limit approaching from the right. And that's how we're going to split up this function right here. So doing the actual integration, we still have this limit. C approaches 2 from the left. Negative 1/3 will leave me with a positive 2/3 when I add 1 to it. I take a reciprocal of 2/3, I get 3/2. So I have 3/2 x minus 2 to the 2/3 from 1 to c. And the exact same for the other integral, now just with my limits different. So 3/2 x minus 2 to the 2/3, now from d to 10. Plugging in my values, I get the limit as c goes to 2 from the left of 3/2 c minus 2 to the 2/3 minus 3/2 1 minus 2 to the 2/3, and similarly limit as d goes to 2 from the right, 3/2 d minus 2 to the 2/3 minus 3/2 10 minus 2 to the 2/3. Okay, so now let's talk about what these limits are going to do. Because at no point in this limit right here I am dividing by anything remotely close to 0, I'm just taking something that's going to get closer and closer and closer and closer to 0 as the c approaches 2 raised to the 2/3. This is going to turn into a 0. If instead I had something like 1 over c minus 2, this might approach either positive or negative infinity because I am dividing by 0. But in this case, it's just multiplication and taking powers of something getting close to 0. So that means the entire function itself is going to get close to 0. And similarly with this limit as d goes to 2 from the right. So the two parts with the limit are going to be 0. So I have minus 3/2 of negative 1 to the 2/3 minus 3/2 of 8 to the 2/3. Oh, and I actually have these switched by accident. So this should be a 10 in this one right here because 10 is my upper bound, and this one should be a d. So all that does for this next part is it changes that from a negative to a positive. So 8 to the 2/3. Negative 1 squared is 1. Cubed root is 1. So I have a negative 3/2. Cubed root of 8 is 2, right? 2 times 2 times 2 is 8. I square 2, I get 4. So this is plus 4 times 3/2, which if you simplify this out is going to give me 9/2 as my final answer. So this integral I have here, even though my function values are going to go up all the way to positive infinity, and even though my function isn't continuous here, I am able to take the integral and get a finite solution. So that is how you deal with improper integrals. Generally, you'll introduce limits of some kind, you'll solve the integral as you normally do, and then deal with what the limit is actually going to be.